Hello friends, welcome to Lesson 5 on electrical machines. In this lesson we will study the DC motor characteristics, that is torque armature current characteristic, speed armature current characteristic and speed torque characteristic. Let us start by defining, what is DC motor characteristics? It's a graphical representation of how a DC motor's performance parameters relate to each other. The parameters are such as speed, current and torque. The characteristics are 1. Torque and armature characteristic, also known as the electrical characteristic. 2. Speed and armature characteristic. 3. Speed and torque characteristic, also known as the mechanical characteristic. Importance of the characteristic curves. 1. They help us understand the behavior of the motor under different operating conditions. 2. They guide us in selecting the right motor for a particular application. Torque and armature characteristic. This is a curve between armature torque, Ta, and armature current, Ia. Speed and armature characteristic. This is a curve between speed, N, and armature current, Ia. Speed and torque characteristic. This is a curve between speed, N, and armature torque, Ta. Let us start off by looking at the torque armature current characteristic of a shunt DC motor. Referring to our video on electrical machine lesson 4, we said that flux in a shunt DC motor is constant. Therefore, torque increases linearly with armature current. The torque armature characteristic is a straight line passing through the origin. Note: a shunt motor should not be started under heavy load since high current is needed to drive the load. The below is a graph of torque armature current of a DC shunt motor. In ideal situation, when flux is constant, the graph is as shown by the blue dashed line. When flux is mild weakening, practical scenario, the graph is as shown by solid curve. Now let us look at torque armature characteristic of a DC series motor. We will look at two scenarios. 1. At low armature currents, after magnetic saturation, flux is directly proportional to armature current. Therefore torque is directly proportional to the square of armature current. Thus starting torque of series is very high than for shunt motor. Thus torque armature current characteristic is a parabola. 2. At higher armature currents, saturation region, flux, is no longer proportional to current. Flux becomes almost constant, torque is directly proportional to armature current. The torque armature characteristic curve bends and becomes approximately a straight line. The below is a graph of torque armature current in a DC series motor. At low currents there is a quadratic rise in torque. At high currents torque increases almost linearly with the current. Now let us look at torque armature current characteristic of a compound DC motor. Compound motors. There are two types. 1. Cumulative compound. In this type of motor the magnetic field produced by the shunt winding adds to the field produced by the series winding. 2. Differential compound. In this type of motor the shunt field winding's magnetic field opposes the series field winding's magnetic field. Cumulative compound. At low currents, shunt field dominates, so flux is nearly constant. As load current increases, series field adds extra flux, so torque rises more sharply than in a shunt motor. Thus torque is directly proportional to armature current. The curve is slightly steeper than a shunt motor curve, and approaches series motor behavior under heavy load. The below graph is of torque armature current in a DC cumulative compound motor. At low currents the starting torque is high. At high currents the torque curve flattens, similar to shunt motor. Now let us look at the torque armature characteristic in a differential compound DC motor. Differential compound motor. At low currents, torque is directly proportional to armature current, similar to a shunt motor. As current increases, series field opposes shunt flux, net flux decreases and torque increases more slowly and may even fall. This makes the motor unstable at high load, so it's rarely used. Its curve starts like a shunt motor but bends downward. Now let us look at the speed armature characteristic in a shunt DC motor. Shunt motor. Flux is almost constant because the field winding is connected in parallel with the supply. As load increases, armature current increases. Due to armature resistance drop, back EMF slightly reduces, causing a slight drop in speed. Hence, the speed remains nearly constant. From no load to full load. Note: shunt motors are called constant speed motors. The below graph is of speed armature current in a DC shunt motor. Since flux is nearly constant, thus speed remains constant across varying loads. As load increases, armature current increases and there is a slight drop in speed. Here we will now look at the speed armature characteristic of in a DC series motor. Series motor. At low armature current, light load, flux is very small because armature current is small. From the equation of speed is directly proportional to back EMF and inversely proportional to flux. Speed becomes very high, thus series motor must not run without load. Speed armature current characteristic is a hyperbolic up to magnetic saturation. After magnetic saturation flux and thus speed is constant. The below graph is of speed armature current in a DC series motor. At light load flux is small because armature current is small and thus speed becomes very high. Here we will look at the speed armature current characteristic in a cumulative compound DC motor. Cumulative compound motor. Total flux increases as armature current increases. As load, armature current, increases, flux increases slightly, speed decreases more than in a shunt motor. Characteristic curve lies between shunt and series motor curves. Has a better starting torque than shunt. The below is a graph of speed armature current characteristic of a cumulative compound DC motor. As load current increase, flux increases slightly and speed decrease more than in shunt motor. Now let us look at the speed armature current characteristic in a differential compound DC motor. Differential compound motor. The flux decreases as load increases. As load, armature current, increases, flux weakens and speed rises dangerously. This makes the motor unstable under load. Differential compound motors are rarely used in practice. Now let us look at the speed torque characteristic of a DC shunt motor. Shunt motor. At no load, torque is very small, current is minimal, so speed is almost maximum. As load torque increases, armature current increases, voltage drop increases, back EMF reduces and speed slightly decreases. Because flux is constant, the reduction in speed is small. Even with varying load torque, the motor maintains nearly constant speed. The below is a graph of speed torque characteristic of a DC shunt motor. Even with varying load the speed is nearly constant. Now let us look at the speed torque characteristic of a DC series motor. Series motor. At light load, armature current is small, flux is small and speed becomes extremely high. At moderate load, as torque demand increases, current increases, flux increases and speed decreases significantly. At heavy load, torque is high, but speed drops steeply. Speed torque curve is a rectangular hyperbola, very high speed at low torque. Steeply falling speed as torque increases. Below is the graph of speed torque characteristic in a DC series motor. The speed is steeply falling as torque increases. Now let us look at the speed torque characteristic of a cumulative and differential compound DC motor. Cumulative compound characteristics. Higher starting torque than a shunt motor. Better speed regulation than a series motor. Widely used in practice. Speed falls moderately with torque. Differential compound characteristics. Speed increases with load, unstable. Rarely used in practice. Speed rises with torque, unstable. Thank you for watching our channel. Please don't forget to like, comment, share and subscribe. May God bless you.